And remember, the octet rule says that atoms want 8 electrons in their outermost orbit. So this is a great way to look at the exceptions to the octet rule. There are things called incomplete octets, meaning that the central atom doesn't quite get 8. There are expanded octets, meaning that the central atom actually gets more than 8. And then we have situations where one central atom is willing to donate both of its electrons to something else, and the other one doesn't have to contribute at all. And that's called a coordinate or dative covalent bond. And so that's what we're going to look at. So let's first look at boron trifluoride. Notice the central atom is boron, and it has 3 fluorine. This is the ball and stick structural form for you. The next one is phosphorus pentachloride. This is the space filling model, and there's phosphorus down deep inside there, and then 5 chlorine attached to it, and then ammonia. So we'll look at those a little bit closer. The first one is boron trifluoride. So here is our ball and stick. So you can see 1 boron and 3 fluorines. Now let's draw the Lewis model, the Lewis structure, so that it might be a little easier for you to see how it is an incomplete octet. So we're going to start with our central atom, which is boron. Boron is in group 13, so it has 3 valence shell electrons. 1, 2, 3. Fluorine is a halogen, meaning that it's in group 17. So each fluorine wants 1 electron. So we'll go ahead and position the 3 fluorines around the boron and draw in the electrons for fluorine. We have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. So you can see that boron only has 1, 2, 3 pairs of electrons around it. And then the fluorine satisfies the octet rule. It has the 8 electrons around it. When we go to draw the Lewis structure, we're going to again put the boron in the center and put our 3 fluorine. And then we're going to show the shared pairs with a line. So we'll draw in those shared pairs. And again, boron is incomplete. It does not have all 8 electrons. And then we just draw in the lone pairs. Each fluorine has 3 pairs of lone electrons, 6 lone electrons altogether. But because they're in pairs, they're satisfied the way they are. So there's the Lewis structure for boron trifluoride, which is an incomplete octet. Now let's go on to the next one, which is phosphorus pentachloride. Here is our space filling model, and we have the phosphorus as our central atom, and then we have the fluorine all around that. So we're going to start out with our central atom, bring it down, and phosphorus is in group 15. So it has 5 valence shell electrons. 1, 2, 3, 4, 5. And fluorine is in group 17. Each fluorine wants 1. So we'll position the fluorine. 3, 4, and 5. See how each fluorine shares 1 of the phosphorus electrons. Now we draw in the electrons for fluorine. 1. Change the color on that one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Fluorine has, each of the fluorine has 8 now, and phosphorus has an expanded octet because it actually has 5 pairs of electrons, making a total of 10 electrons in its outer orbit. That is an exception to the rule, but it is a great way to add diversity to these molecules. Now the last one we're going to look at is the dative or coordinate covalent situation. And here we have ammonia. Notice it's not like the ammonium. Ammonium has the extra hydrogen and it's charged. This is ammonia, nitrogen trihydride. We'll put the central atom in there. And nitrogen is in group 15, so it has 5 valence electrons. And then we bring in the hydrogens. Each hydrogen wants 1 electron, so it is willing to share with nitrogen. Now nitrogen is complete and each hydrogen is complete, but notice there is a pair of electrons right here that doesn't have anything near it. So that pair of electrons is actually available for something else to come along and share. So that pair of electrons would be up here. And when we talked about VSEPR or VSEPR model, these valence shell electrons actually repulse these bonds, and that's what pushes them down and creates a pyramid shape instead of a planar shape. So that lone pair is important. That lone pair is available for something else to come along and hook onto, like say oxygen needs to, so it can hook onto it. And the most common one is, yes, the way we form the ammonium ion. Positive hydrogen comes along with no electrons and says, I really need a couple electrons in my outermost orbit, so I can share both of those. And then we get the ammonium ion. Remember, that's what happens in solution. So you have to have the electrons available to move in solution. I hope that helps you, and I'm looking forward to the next time. This should complete molecular shape, and if you have any questions, make sure you come and see me. The sooner the better. Have a great day. Goodbye.